Hi everybody, this is Dr. Nigro with a Physics Fundamental Screencast. This one's going to be focused on vectors and utilizing trig functions as part of our calculations with vectors. If you have questions about basics for vectors, please go check out my Basics Vectors Screencast. All right, when we have trig functions, that tends to mean we've got a triangle around, usually a right triangle. So I'm going to draw one right here. All right, and this right triangle is going to have a horizontal, a vertical, and then tip to tail resultant. So the red represents my resultant. This leg to the right represents my horizontal component, and then up represents my y component. Now we can obviously draw this triangle many different ways, all right? But we connect the x and the y tip to tail, and then the resultant goes from the origin to the final tip of our vectors. All right, now we have an angle here called theta, all right? And this angle will always connect our initial vector to our resultant vector. All right, now Pythagorean's theorem is very handy with right triangles. We know that r squared, that resultant value, has to equal, in this case, x squared plus y squared. All right, so in other words, our hypotenuse squared has to equal our adjacent leg squared plus our opposite leg squared. All right, now we can solve that, at least for r, by moving the square, by taking the square root of both sides, and then we end up with the resultant value is going to be equal to the horizontal piece squared plus the vertical piece squared, and then we take the square root. All right, now I'm using r, x, and y here, generally speaking. All right, these can be velocity values, they can be acceleration values, they can be displacement values, or we could even have force values in here. The key is they must all match. All right, what does that mean? It means no mixing and matching. All right, you can't have your horizontal component be a velocity vector and your vertical component be an acceleration vector and hope to find the resultant. That does not work. All right, so both components have to be velocities or accelerations or displacements or forces. No mixing and matching. All right, now the other piece that we can utilize our right triangles for is using our trig functions. All right, and the handy device for memorizing or remembering these is SOHCAHTOA. All right, now we'll talk about what each of these means specifically in just a second, but I want to go back to theta quickly. All right, remember, theta is the angle we'll be dealing with for our functions here. All right, and it is specifically the angle between the resultant and the first vector. All right, so that's how we define theta. All right, so let's draw a right triangle again. Horizontal and vertical, we'll connect it. All right, so again, we've got our resultant, and then we've got our y component and our x component. All right, so let's start with SOA. All right, so we know that the sine of our angle, which is here, is going to be equal to the opposite leg divided by our hypotenuse. All right, and remember, this is our opposite leg, directly opposite of that angle. All right, and then the resultant represents our hypotenuse. All right, so in other words, for our purposes, the sine of theta will always equal the y component divided by our resultant. All right, now let's move on to our CA. So that's our cosine function. All right, and our cosine function is always equal to the adjacent leg divided by that hypotenuse. All right, and for us, our adjacent leg is our horizontal piece. It is adjacent to the angle. All right, so cosine of theta will always equal the x piece of our triangle, the horizontal component, divided by that resultant. All right, and then finally, the tangent function. So the tangent of theta is equal to our opposite leg divided by our adjacent leg. And in our triangle, the opposite leg will be our vertical divided by our horizontal, or y divided by x. All right, so understanding how to use Pythagorean's theorem and then remembering what SO, CA, and TOA mean are going to be very useful when we start building our vector maps. All right, so let's do a little bit of practice. We'll try a couple different ways. We're going to start by using the Pythagorean theorem to find the magnitudes, and these are our velocity values for the following vectors. All right, so we have two components, a horizontal and vertical one, and then we've got our connecting resultant vector. All right, so here's our vertical component. Here's our, I said that backwards. That's our horizontal component. Here's our vertical component, and this is our resultant between the two. All right, please notice the tip to tail addition and that the resultant is going from that origin to the final tip, which puts theta right here. Okay? All right, so our resultant squared is going to be equal to the x component squared plus the y component squared. If we take the square root of both sides and plug in our values, then we're going to have 9 meters per second squared for our horizontal piece and 4 meters per second squared for that vertical piece. Well, actually, technically, this should be -4 because it's pointed down. Right, so let's just put that in. It doesn't really affect the mathematics because we're squaring it, so the negative goes away, but it is more accurate to put it in there. All right, pull out our calculators, do a little bit of calculation, and we find that we have a resultant vector that is 9.85 meters per second in magnitude. All right, now your resultant vector should be greater than each of the two legs, all right? But generally speaking, should not be any more than the sum of those two legs. It's just a good rule of thumb. All right, now directionally, we could figure out theta. We could use tangent, all right? But we're just using Pythagorean's theorem here. So I'm just going to say, in general, to the southeast, all right? I can be more specific than that, and if the problem calls for it, you should be, all right? But for now, we're just going to leave it there. All right, now we're going to move to our second triangle, all right? Again, we have an x component, and we have a y component, and then we have a resultant vector that connects the two. And in this case, our angle for theta is here, all right? The calculation is the same. The resultant vector squared should be equal to our horizontal component squared plus our vertical component squared. All right, so we take the square root of both sides and plug in our values. So 30 meters per second squared for that horizontal piece, 10 meters per second squared for the vertical piece. And if we look, we are pointed to the right and up, so both are positive. Plug everything into our calculator, take the square root at the end, and we get a magnitude of 31.6 meters per second. All right, and again, I can use tangent because I know the opposite and adjacent. I can find that angle theta, but for right now, we're just going to generally say to the northeast. Okay, so that's how you can use Pythagorean's theorem if you're given the magnitudes of your component vectors. But what if you're not? What if instead you know the angle theta and you know the hypotenuse? Can we use that information to find the component magnitudes? And the answer, of course, is yes. All right. We know that the angle theta and then the hypotenuse can be used with our trig functions to find these two different pieces. All right. So generally speaking, we know that the sine of theta is going to be equal to our y component over our resultant. All right, so if we rearrange that to solve for y, we find that the y component will be equal to the resultant times the sine of theta. All right, so that's a handy formula to have in your back pocket. All right, we also know that the cosine of theta is going to be equal to our x component over that resultant. And again, if we solve, but this time for x, the x component will be equal to that resultant times the cosine of theta. All right, so remembering these two rearrangements of our sine and cosine formulas makes finding these components all that much easier. All right, so let's start with our first triangle. All right, we have a resultant value of 7 and a theta angle of 40. All right, so if I want to find the y component, that's going to be equal to that resultant value times the sine of theta. All right, so y is going to be equal to 7 times the sine of 40 degrees. So I get my calculator out and I make sure that I am in degrees and not radians. Type everything in, all right, and I get a magnitude of 5.4. All right, now I don't have a unit because I'm not given a unit for the hypotenuse, so I'm going to leave it as is, but I can actually list a little bit more about this, all right. I know it's 5.4 in magnitude, but I also have the angle, so I could say at 40 degrees, and I'm going to choose my horizontal piece to be my reference and say north of east. All right, so this would be the full informational piece about that vertical component. All right, let's try our horizontal piece. All right, so x is going to be equal to the resultant times the cosine of theta. All right, so we plug in our value of 7 at cosine of 40 degrees, plug that into our calculator, and we get a value here. Oh, I think I mixed my two values up. I did. Oh, I'm sorry about that. This should have been 4.5. Sorry about that, 4.5. And this should have been 5.4. All right. Now, the reason that's reasonable, to be honest, I should have caught that. All right. Our angle of 40 degrees is not quite halfway between 0 degrees and 90. All right. And so that means that we've got more horizontal than vertical. Once we get to 45 degrees, then they should be equal. And then if you go above 45 degrees, the y component should be larger than the x. So if you keep that in mind, that'll also help you catch some errors. Obviously, I needed a little help there. All right. For our full directional piece, I have 4.5 for my magnitude. And again, it's going to be at 40 degrees. And I've decided to make east my reference point, so north of east. All right. All right, so let's move on to our second triangle here. All right, this time I've got theta here. Again, x and y pieces, and I'm going to be looking at a magnitude of 20 for that resultant. All right, so if I have an x component, that's going to be that resultant times the cosine of my angle. So in this case, 20 times the cosine of 15. All right, plug that into my calculator and I get 19.3 for the magnitude of that vector. And then if I utilize my angle and give the full direction, I get 19.3 at 15 degrees, and I'm to the south of east here. Okay, I'm going to move this up. Oops. Just so it's out of the way. Right, and then I'm going to end with my vertical component. So y is equal to r times sine of theta. All right, so I'm going to have a y value that is 20 times the cosine of 15. All right, I'll plug that in my calculator. I get 5.18 for the magnitude, but this vector is pointing down, so that should be negative. All right, so I'm going to put a negative sign in here. If I had used this angle, all right, I would have gotten a negative sign. All right, but because we plugged 15 in, then we're going to get it positive, and we just have to recognize. All right, so it should be negative 1.58 at, again, 15 degrees south of east. All right, so that's an example of how to use the sine and cosine functions to find these two component legs. All right, now let's try a couple problems because I think that these make a whole lot more sense if you try some problems. All right, so here we have a climber who is working her way up a cliff. All right, if she moved 3.2 meters to the east, then 20.1 meters south, how far away from her starting position is she? All right, so we've got two directional pieces. We've got a horizontal piece and we have a vertical piece. So we're going to draw those as vectors, trying to do our best to be relatively in the right size, and then we'll connect with our resultant. All right, so we're moving to the east 13.2 meters and then down a little bit further at 20.1 meters. So 13.2 meters east, 20.1 meters south. And then our resultant will connect our origin to our final vector. All right, so these are meter values. So this is our displacement, and this will be our resultant for that displacement. All right, our initial vector is the east one, which makes this our theta angle. Okay, so the question first is, what is our magnitude? All right, so we know that the change in position for that resultant squared will be equal to the change in position of our horizontal piece squared and the change in position of our vertical piece squared. All right, so just Pythagorean's theorem. We're going to take the square root of both sides and plug in our values, and we have 13.2 meters squared for that horizontal piece, negative 20.1 meters for our vertical piece, because that piece is pointing south. All right, plug it into our calculator, and we find that the resultant value for our change in position is 24.0 meters. All right, now, when asked how far away, we should indicate our angle here. So we are going to take a second this time and find out what theta should be. All right, so I have the horizontal and vertical components. So tangent is going to be a good method here. So the tangent of theta is equal to the y component divided by the x. All right, and this time I'm looking for tangent. So I need to take the inverse tangent, or the arctan, of both sides. So I'm going to say that theta is going to be equal to the inverse tangent of the y component divided by the x component. All right, and then I'm going to plug them in. So theta is going to be equal to negative 20.1 meters, that's our y component, divided by 13.2 meters, our x component. And when I plug that into my calculator, it comes out as a negative 56.7 degrees, which makes sense because we're below the 0 degree line. All right, you can rewrite this as 56.7 degrees, and you can say south of east, and that means the same thing. All right, so if we want to correctly write our vector, all right, then we're going to write it as 24.0 meters at 56.7 degrees south of east. Okay, so that will be the correct information for that one vector. All right, let's look at this next one. All right, a startled bird flies to a branch that is 35.2 meters away at an angle of 20 degrees. All right, and let's specify this is above the horizontal. All right, because without that information, you don't really know where that 20 degrees is in reference to. All right, so now we're going to draw that vector. Just in general, it'd be about like this, 20 degrees above that horizontal, all right, which means we can draw in our two vector components. It would look something like this, right, where this is our x component and this is our y, and this is going to be our resultant piece, all right. Now the resultant piece has a value, it's 35.2 meters, all right, so this is an example where we know the angle theta and we know the resultant value, so we're going to use those to find our vertical and horizontal components of this displacement. All right, so we're going to need to pull up our SOHCAHTOA. All right, so we remember that the y component is equal to the resultant times the sine of our theta angle. All right, so in this case, y is going to be equal to 35.2 meters times the sine of 20 degrees. All right, so we're going to plug that into our calculator, and we find that the displacement for the y component, or the vertical displacement, is 12.0 meters, and that is directly north. All right, so 12 meters north would be our vertical displacement. All right, for our x component, it's the resultant times the cosine of our angle. So we're going to have x equal to 35.2 meters times the cosine of our angle of 20 degrees. Plug that into our calculator, and we get a value of 33.1 meters, and this is going to be due east. All right, so these are our two vector components. All right, you can see that the directional piece is in there because they are east and north. There's no middle, there's no angle in there. Okay, all right, let's try one more. Right, this one, Pikachu sees a Pokeball 50 meters away at an angle 35 degrees above the horizontal. All right, he runs straight to that Pokeball and he does it in 9 seconds. Okay, draw a sketch of Pikachu's motion. All right, so 35 degrees above the horizontal, it's a little bit like that. All right, then I'm going to draw my two components, my x component and my y component. This is going to be my angle of 35 degrees, and I've been given the resultant value, the displacement for that resultant of 50 meters, all right? So the first question is, well, how fast did Pikachu move? All right, so we know the velocity for that resultant, all right? We also know the time, all right? So we know it was 50 meters and it took him 9 seconds to get there. So with that information, we should be able to find that displacement value. All right, we know that the average velocity is equal to the change in position divided by time. So our change in position is going to be equal to the average velocity times time. All right, so we plug in, oh, I just did that backwards. I'm sorry. I'm mixing up my displacement and my velocity values. All right, let me try that again. All right, we know the displacement, sorry. The resultant displacement is 50 meters for 9 seconds. All right, so we're looking for our velocity. It does say how fast. All right, so we know that the average velocity is equal to that change in position divided by time. All right, so our change in position is 50 meters. It took Pikachu 9 seconds to cover that. All right, so that tells me that my velocity for that 50 meters must have been 5.56 meters per second. All right, now this is the velocity for the resultant leg. All right, and that's important. You have to keep track. If we use the displacement on the resultant to find velocity, then we found the velocity on the resultant, okay? All right, the next part of the question wants to know what are the components of the displacement. So this is our x and y component, all right? So that change in position vertically or horizontally is going to be equal to my resultant times the cosine of my angle, all right? So the change in position for x is going to be equal to 50 meters times the cosine of 35 degrees, all right? So I plug that in my calculator, and the change in position in the horizontal direction is 41.0 meters, all right? And this is, we're just gonna list it as east. It didn't specify whether it was left or right, so we're going with east. All right, we're gonna repeat, but we're gonna find the change in position vertically. This is gonna be equal to the change in position of the resultant times the sine of theta. All right, so that change in position is going to be equal to 50 meters times the cosine, oh, not cosine, I just said sine, times the sine of our 35-degree angle. All right, plug that in our calculator, and we have a vertical displacement of 28.7, and we'll just point that north, again, because this problem did not specify which way we were going. Well, it said above the horizontal, so that's definitely going to be north. The east one, you have some argument for which way that's going. All right, so now it says, what are the components of Pikachu's velocity? Okay, so we just did the components of the displacement. So I could fill in this triangle, right? I could put 28.7 meters north and 41.0 meters east, right? And with that information and the time of 9 seconds, I can use each leg plus the time to figure out what that velocity is. So let's try it that way first. All right, so in other words, we're going to use our average velocity formula to solve for the component velocities. All right, so our average velocity in the x direction is going to be equal to the change in position in that x direction divided by time. All right, so v sub x is going to be equal to 41 meters divided by 9 seconds. All right, if we plug that in, we find that that average velocity horizontally is going to be equal to 4.55 meters per second. All right, we're going to repeat, but this time we're going to find the average velocity vertically. All right, so that's the change in position vertically divided by time. And we found that that change in position vertically was 28.7 meters, and we divide that by our 9 seconds, and we get an average vertical velocity equal to 3.20 meters per second. All right, so that's one way to do it, just using our average velocity formula. The other way is to use our SOHCAHTOA, or SO and CA rather. All right, so we're going to use SOH and CAH. All right, so if we're looking for the vertical component of our velocity, that's going to be equal to the resultant velocity times the sine of theta. So that vertical velocity is going to be equal to 5.56 meters per second times the sine of 35 degrees. All right, so we plug that into our calculator and we get, oh, how convenient, 3.20 meters per second. The same thing we got using the other calculation style. All right, and then if we repeat, but this time for the horizontal piece, we need that resultant velocity and the cosine of our angle. Plug those values in, so we put in 5.56 meters per second and the cosine of 35 degrees, and we find that our horizontal velocity must be 4.55 meters per second, which is the same. All right, so there are two ways to calculate here. We can use our average velocity formula, or we can use our trig functions, okay? All right, so those are just a couple different examples. Let me know if you have any questions, and I'm happy to help.